Welcome to solverfy.
Okay, in this problem we have 2 points, A and B. A is located 26 centimeters north of a point charge of charge big Q, and B is located 36 centimeters west of the charge. This is a negative charge with 3.8 microcoulombs, so its electric field is going to be pointing inward towards the charge. So to start off, we need the potential and the electric field due to a point charge. In that case, it's simply V equals 1 over 4 pi epsilon naught Q over R. And for the electric field, it's simply 1 over 4 pi epsilon naught Q over R squared radially inward. So to find a potential difference, we really just need to, really the only thing that's going to matter is the difference in radius away from this point charge. So to jump into it, for part A, VB minus VA is really just the potential at point B, which is this, minus same expression for RA. We can combine some things to make the algebra a little bit easier. We can pull the Q value out, keep all these constants together, and really we just have a difference in inverse radii. So when you plug in the distances away for point B and point A and the magnitude of the charge, we will end up with a result of about 3.6 times 10 to the 4 volts, or 36 kilovolts. For the second part, things are a little bit more complicated because the electric field is pointing in different directions. For B, the electric field is given by 1 over 4 pi epsilon naught magnitude of Q over RB squared. And because it's west of the point charge, it's going to be located in the I hat direction. So this would be like on an x-axis, it's on the horizontal. For A, the point A is located to the north of the point charge. So we're going to have same magnitude charge over the radius up to A squared, but now it's in the j hat direction, the negative j hat direction rather. So we need to put a negative sign right there. And this reflects the fact that the electric field points inward towards the point charge. So the difference in electric field is simply the vector subtraction between these two things. And if we plugged in some numbers for all of our values, we'd have 2.636 times 10 to the 5 volts per meter in the I hat direction, and 5.05 times 10 to the 5 volts per meter in the j hat direction. We can get a magnitude of that. Once we have this new vector, we can get a magnitude of it. The magnitude of this electric field difference vector is like the magnitude of all vectors. It's simply going to be the x component squared plus the y component squared. We can plug in our numbers, and we will end up with a value of about 5.7 times 10 to the 5 volts per meter. That's the magnitude of our electric field difference vector. And of course, to do an angle between the two vectors, we can take an arctangent, which is simply EA over EB magnitudes, which would come out to be about 5.05 times 10 to the 5 over 2.63 times 10 to the 5. We can plug this into our calculator and we will end up with about 62 degrees. Okay, and that's it.